Yes, so today's video to be solving questions using our steam table if possible. Now the question says that the feed to a compressor, so this our compressor, is superheated steam. So now we've been given the idea that it's superheated steam at 300 degrees Celsius and 20 bar absolute pressure. It enters the compressor at a velocity of 20 meter per second. The moment you see a velocity, then you should be in your mind that definitely kinetic energy isn't zero. The pipe inside diameter, so this the pipe, the steam is entering to the pipe. The pipe inside diameter is 0.1 meters. The discharging pipe after the compressor has a smaller inside diameter, and the discharge velocity is 170 meter per second. So the inside has a smaller diameter, but they didn't give us that diameter. The heat loss from the compressor to the surrounding, so heat is lost from the compressor to the surrounding is 5 kilowatts. So heat loss is negative. The exit of the compressor is superheated. So now the exit is also superheated to 50 degrees Celsius and then 60 bar. The heat loss from the compressor to the surrounding is 5 kilowatts. Determine the compressor horsepower. Now the compressor horsepower is simply the work done by the compressor. So this is an open system because of the compressor. And so Q minus WS is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. Yes. So now we realize that this is in kilowatts, so we need to multiply this by the mass unit. Right? But then the mass unit wasn't given the question. Yes, the mass unit wasn't given the question. So now how do you find a mass unit? We know that mass fluid, right, is equal to density times volumetric fluid. But mass weight is in kilogram per second. Density is in kilogram per meter cube. And then volumetric fluid being meter cube per second. And meter cube, so this cancels. We are left with kilogram per second. Now, how do you find the density? In some advanced cases, because it's a steam, some people tend to use density of water to be 1000 kilogram per meter cube. But then, because we are dealing with steam, you can't actually see that the steam has the same density of that of water because you know temperature affects density. Right? So what we have to do is that from this, eh, from this, we know that density is actually kilogram per meter cube. Now 1 over density will give us meter cube per kilogram, and that is specific volume, right? And now from this specific volume, we can read from the steam table. So we can say our mass fluid is equal to our volumetric fluid divided by our specific volume. Now I'm going to give it volumetric fluid. But you know volumetric fluid, the unit is meter cube per second. And that is actually equal to area meter squared times velocity meter per second. And that will give us meter cube per second. Right? So we can see that our mass fluid is equal to area times velocity divided by specific volume. Now this is velocity, this is area, and this is specific volume. When you want to find the mass fluid, when you do a material balance, you realize that M1 is equal to M2. Inlet stream is equal to our outlet stream. So you can use the inlet stream condition to find our M1. Or better say, you can use the outlet stream condition to find our M2. And then we can repeat it. They are still the same, is equal to M. But then, we need velocity, right? We have the velocity. We need area, right? I'm thinking of using the outlet stream. So now we need velocity, right? We have our velocity. We need area. We don't have any diameter to calculate for the area, so you can't use the outlet stream. So now let's use our inlet stream. We have area, right? What's the diameter? you can find our area to be pi d squared over 4. So 3.142 multiplying diameter 0.1 squared all over 4. So 0.142 times 0.1 squared all over 4. So we get 0.007855 meter squared. That is our area. Our mass fluid now becomes our area 0.007855 times the velocity was 20 meter per second all over the specific volume. Now how do you find our specific volume? For our specific volume, we know that the steam engine is superheated. So we'll go to our steam table. And it was occurring at 300 degrees Celsius and 20 bar, 320 bar. So we go to our steam table. We go to our superheated part, 300 degrees Celsius and 20 bar. So 20 bar, 300 degrees Celsius. So 320 bar. So now, this is our specific volume V, and then we can confirm from here. Right? No, you just know that these are specific volume. Right? So our specific volume is at 300 degrees Celsius is 0.1255. We go back to our question. 0.1255, and then we can find our mass fluid to be 0.007855 times 20 all over 0.1255, and then we get our mass fluid to be 1.252 kilogram per second. So that's what we get. So now we have our mass fluid. Now that we have our mass fluid, what do we need again? We have our mass fluid. We have to find our change in kinetic energy. Our change potential energy will be zero, but the question didn't give us any information on the equation. So our energy balance becomes Q minus W is equal to M multiplying change in enthalpy H2 minus H1 plus change in kinetic energy. Now let's find our change in kinetic energy. Our change in kinetic energy will be half V2 squared minus V1 squared. Now because we factorize our M out, so we will multiply by the M. So, and then from our previous video, if you want to convert it into kilojoules per kilogram, of course this will need to be in kilojoules per kilogram. Before you can get it in, this will be in joules per kilogram. Before you want to convert it into the kilojoule per kilogram, you have to divide by 1000. Right? So from our previous video, that was what we established. So we have multiplying V2 170 squared minus V1 20 squared all over 1000. So change in kinetic energy becomes minus 20 squared all over 1000. So change kinetic energy becomes 14.25 kilojoules per kilogram. Now we'll come back to our change in enthalpy. The question asks us to determine the compressor horsepower, which is our work. We know our heat, we know our mass fluid. Now we know our change in kinetic energy. So we have to find our change in enthalpy. H2 is equal to. Now the question says the steam leaving is superheated. So it becomes very easy. You just have to read 60 bar at 350 and read the enthalpy there. And then at H12 it's also superheated. So 20 bar 300 degrees Celsius with our enthalpy. So 350 and 60 bar. I think for the 20 and 300 we read about it from the side. So for the enthalpy would 3025. 3025 for each one. 3025. And then for 60 to 350. 60 and 350. Now let's trace this 350. This 350. And then there are 60. Alright, so we are reading from this values. Enthalpy is this. So that would be 3045. Let me expand it. That was 3045 to 3045 kilogram kilojoule per kilogram. And it's also kilojoules per kilogram. And I will just go back to our energy balance equation. This is our first law of thermodynamics, and then we find our work. So what you are left with is just doing simple substitutions to find our work. So our Q was -5 minus our W is equal to our mass flow rate. We add it to 1.252. Change in enthalpy now becomes 3045 minus 3025 plus our change in kinetic energy, which was 14.25. So now our work becomes, so we can let this one come here, and then we transpose the whole of this to the other side. The -5 minus 1.252. So let's evaluate what's in the bracket. 3025, sorry, 3045 minus 3025 plus 14.25. So we get 34.25. Now our work becomes -5 minus 1.252 multiplying 34.25. We get -47.881 kilojoule per kilogram. Sorry, to be in kilowatts. Why do you think it should be in kilowatts? Because it is 5 years already in kilowatts. And besides, you've multiplied m by that. So multiply m by the whole of this. Now get it in kilowatts so that we can subtract. And so our final answer will be in kilowatts. So this becomes the compressor horsepower. Now when we say horsepower, horsepower is also a unit on its own, which is HP. Right? So we need a conversion factor. So if you know the conversion factor, you can just convert it into horsepower. But for now, this will be our final answer. -47.881 kilowatt.